Hi, everyone. Thanks for joining us today. Welcome to the 112th episode of the Qiskit Live Seminar Series. I'm Maria Violaris, and I'm your host for today's talk, which is with Lia Yeh. I work part-time with the Qiskit community team alongside my PhD, which I do here in Oxford. It's just past 5 p.m. for us here, and while we wait for a few minutes for everyone to arrive, I'd love to know where you're all joining us today. So if you can drop in the chat, in the live YouTube chat, where you're joining from, that would be great. The live chat will be open throughout the seminar, so we really encourage you to drop in questions and comments during the seminar. I'll be monitoring that and can pass them over to Lia during the talk. So before we get started with the seminar, I want to give a shout out to International Women's Day, which was this week on Wednesday, the 8th of March. And we know that promoting gender equality and other kinds of diversity is a really important problem for the quantum field. So one initiative that I want to point you towards is the Qiskit Quantum Women Invited Talk series, where we invite really accomplished and interesting women in the quantum industry to give talks to inspire the next generation of quantum researchers and developers. If you want to join those public webinars, you can check out the description for a link. And the next talk is going to be on the 29th of March by Philippa Rubin, who is a research software engineer at the Science and Technology Facilities Council Hartree Centre in the UK. And that'll be at 8:30 a.m. Eastern Daylight Time. So just checking the chat, we've got people joining us from Michigan, Alabama, Paris, India. So a big range there. Thanks for joining. So now I'll introduce our speaker today, and we'll get started with the seminar. So our speaker today is Lia Yeh from the University of Oxford, who is a computer science PhD student here in the quantum group. So, hi, Lia. And
hi, everyone.
Lia's research focuses on using the ZX calculus and related quantum graphical calculi as a useful language for qudit circuit synthesis and quantum error correction. Lia has bachelor's degrees in physics and computing at the University of California, Santa Barbara, and currently she's working part-time at Continuum. But alongside her research work, Lia is really active in quantum outreach and education. She volunteers for the IEEE Quantum Education and for Quantum Universal Education. And she previously worked for IBM Quantum Education, where she worked on making an introduction to quantum computing using the ZX calculus. And she has also spent time teaching high school students for the coding school. So just before I hand over Lia for her talk, I have a quick story on how we met, which involves this IBM Quantum picnic map. So a few years ago, we were both at a big picnic for graduate students. And as we were leaving, I noticed Lia rolling up this IBM Quantum picnic map. Yeah. And so I went up to her and asked her about it. And then it turned out that we were both quantum PhD students in the same year of our PhDs at Oxford. And we'd also both just started doing internships with IBM Quantum community team as well, which is why she had this familiar picnic map. So yeah, picnic maps are great for networking, is what I got out of that.
Yeah, it was great. Also, it was one of the first few in-person social events that I went to after COVID. Like that was like for a large group of people, not just maximum 6 people indoors.
Yeah.
And then you live with.
Yeah, really big outdoor picnic with it was a good event. Great. So now I'll hand over to Lia to tell us about qudits. So over to you, Lia.
All right. Thank you, Maria, for the introduction. And gosh, I'm really excited to be on this seminar. Thanks for the invitations. So it's actually kind of funny because I've been watching these seminars and never ever imagined I could. Well, not it just didn't imagine that I would like to give a talk here. That's crazy. So this talk will be about how to generalize qubit circuits to qudits. And I would say that at the beginning, it may be a bit more heavy on definitions just because we have to get through notation of what qudit gates, just how to draw them in the circuit model and so on. But I hope there'll be a bit of interactive or part that, a bit of lecture style part, one example somewhere in there. And we can do more in the Q&A part as well. So first, I have a long list of acknowledgements. So this work that I'm presenting here would not be possible without multiple teams working on such like these large research efforts. So all these people from both University of Oxford, from Quantinuum's Oxford office, and other research collaborators. I'd like to thank them. I also just wanted to shout out or mention this talk is my research on qudits and the main focus of my research thus far. But if you have would like to reach out about any questions about my other ongoing research, do let me know. In particular, I'd like to shout out the call for papers is now out for the second Quantum Science and Engineering Education Conference. So this means we do publish proceedings, and it's co-located with IEEE Quantum Week. And as far as I know, it was the first quantum education conference, at least that had published papers, and this will be the second. So I'm quite excited for that. To give an outline of this talk, first there'll be a crash course on the qudit Clifford hierarchy. We'll see what that means. And also a gate set that we call the Clifford+Z gate set, talking about constructing arbitrary multiple controlled Toffolis for qudits. I won't show the complete construction because I think it's not that interesting, but some of the parts of it that I will show I think are really interesting. We'll also talk about prime dimensional ZH calculus. So this is a variant of ZX calculus, which I'll cover both those, and the qudit, so prime dimensional qudit equivalent of Toffoli plus Hadamard gate set. And there's actually a bit more stuff that should be in this outline, but about just some more interesting shout outs to work on ongoing work on qudit and qpit, so prime dimensional qudits, graphical calculi. To start off, I'll define a qudit. This is the d-dimensional generalization of a qubit. So for a qubit, d equals 2. And this is true of many physical systems. So unlike classical computers, where if we would want to just have, like, say, arithmetic modulo 3 or 4 or some other, instead of base 2, like instead of classical computers storing our information and processing them as bits, we would have to redesign most computer manufacturing and all this chip design to incorporate all of this. So all of these features, but for qudits, once we have quantum computers, with quantum computers, we already have these higher energy levels. So I'll just show a transmon energy versus phase modulo 2 pi graph. And this is a nonlinear oscillator potential. But basically, the qubits on a transmon device is that you have this potential, and then you have these energy levels within this potential, and you're just choosing to restrict to just the ground state, so ket 0, and the first excited state, which is ket 1, when you're using it as a qubit. But there's not really anything preventing, and these higher levels, like ket 2, ket 3, and so on, always exist within your transmon device. So not only may people be interested in looking at higher levels for better control of lower levels, but we may want to use these qudits as the native quantum information processing units as well. For some reasons of why we'd want to study them, not only better control for qubits such as noise or leakage. So leakage is when your some you have some state that's in the Ket0 or Ket1 subspace, so it's a qubit state, and then your information leaks to a higher energy, higher level state. So if we could better control the higher level states, we can detect and treat these leakages. But also on less experimental but theoretical side, you also have qudit native algorithms and protocols, and many algorithms and protocols extend to the qudit cases as well. You may also be interested in magic state distillation, which may have better thresholds, or quantum random access memory. So for storing quantum memory, you could get some benefits if you have just more levels in your each quantum information unit. Most of this work will focus on fault tolerance of qudits, at least in the first half of this talk, and most people would believe that to scale quantum computers, they must be fault tolerant, which means they should have some noise tolerance that we can, and also such that we could correct noise faster than it accumulates. So in the qubit case, you have the Clifford gate set, and this is, you can get all of the Clifford gates just by composing C0 gates, S gates, and H gates. These Cliffords generalize to any prime qudit dimension in a very straightforward and systematic way, which I'll go over these definitions. And they're just like in the qubit case, for all these prime dimensional qudit Clifford gates, they're efficiently classically simulable, but they're not enough for universal quantum computation. So it means we need to add at least one non-Clifford gate in order to achieve universal quantum computation. To define what is the qudits versions of polys, so qubit polys are just the X gates and the Z gates and multiplying them together, applying them enough times. So for qudits, let's first define omega to be the dth root of unity. So that's e to the 2 pi I divided by d. And the conventional generalization of polys to prime qudit dimensions, this one's called the Heisenberg-Weil generalization, just cycles these, they're called the clock and shift operators because the shift operator is just you're shifting all the computational basis states, so Ket0 to Ket d-1, so d total. You're shifting them to be addition by 1 mod d. So, and then for the Z gate, this is called the clock operator because you can imagine you have a clock with D hands and then you're just going around ticking this clock. Sorry, D numbers on the clock and you're just ticking around this clock. If you visualize the any complex number of norm 1 as just going around a unit circle in the complex plane. So for qubits, this is our typical notion where the X gate sends Ket0 to Ket1 and Ket1 to 2 mod D, where D is 2, so Ket1 gets sent to Ket0. And for the Z gate in qubits, then when K is 0, then you just have omega, which is to the power of 0. And then when you have K is 1, you get e to the pi I, which is -1. For qutrits, you see that it sends every basis state, so each row, to just, this is like off diagonal of the this is just like the diagonal right below this diagonal, and then also one element up here for the X gate. And for the Z gate, it's just looks like diag 1 omega squared, omega cubed if you had more, if this was d equals 4 or some higher dimensions, and so on. So this can also generalize to Cliffords. We've only talked about polys, so X and Z so far. But so we have some properties that will help us define the Cliffords. So just like in qubit case, X squared is the identity and Z squared is the identity. But for qudits, it's actually X to the power D, so applying the X gate D times in a row. And same for the Z gate is identity. You also have a Hadamard gate that is a discrete quantum Fourier transform. So it basically sends X basis states to Z basis states or vice versa, depending on if it's Hadamard or Hadamard dagger. So the Hadamard gate is not self-inverse, so not self-adjoint, for any prime qudit dimension except for 2. So that's why we need to have this dagger sometimes. We also have that if you commute a Z gate and an X gate, then the phase that you get, this global phase, is a phase of omega, which is the dth root of unity. And these kind of commutation relations is how the Cliffords is defined for any prime qudit dimension. In fact, it's actually a hierarchy of Cliffords. So this has been well known in the literature for, I think before I was born, but a few decades. I think 2 decades. I think after I was born. I think it was 1999 by Gaussman. The first level is the polys, so this X and Z's and phases of omega. And then the second level is the Cliffords, which we'll define shortly. And the nth level is defined recursively with respect to the previous level. So if you commute a gate in the nth level of the Clifford hierarchy with a poly, so X's and Z's, any poly, then the correction that you get from this commutation is always going to be in one level lower in the Clifford hierarchy. So in particular, this is why there's a lot of interest in the T gate in qubits, and the T gate also extends to prime qudit dimensions. The interest in T gates is because if you commute a T gate with a poly, so with an X or a Z, then the correction you get is Clifford. It's because T gates are in the third level of the hierarchy, and polys in the first level, Cliffords in the second level. And the Clifford gates are efficiently classically simulable, and we can correct them efficiently. So this is why people are interested in the T gate. They can distill good T gates and then inject them into circuits via magic state distillation and injection. And this injection uses this fact that it commutes well with polys. So maybe I will not get too sidetracked with this, but it's quite cool. To define here I'll just show, actually this should say qudit Cliffords instead of qutrit Cliffords, but it does work for qutrits, but it's more general, any prime qudit dimension. So the Hadamard gate is defined this way. It sends a basis state, so where k is in the integers mod d, so k could be 0, 1, 2, or anything until d minus 1. And it sends to this omega to the power of, sorry, these should be flipped around. This top one should be S and this bottom one should be H. These are just the Brockett notation definitions. But we won't have to worry about these definitions for this talk because we'll describe them just based off their relations to the other generators of the calculus. And this CX gate is, it's useful for us to understand this because this is one specific generalization of the CX gate that you could do from qubits to qudits. This is specifically the generalization that is Clifford. So if your control is in the computational basis state C, then and your target that's input to the CX gate is in the computational basis state T, then the output target state after the CX gate would be C plus T mod D. So this CX gate in the literature could also be called or referred to as the sum gate because it adds the C gate and the T gate, sorry, the C state and the T state modulo D, where C and T are computational basis states.
Lia, can I jump in with a question?
Oh yeah, go ahead.
David asks, is it reasonable to use qudits for physical quantum digits and qubits for logical quantum bits?
This is actually quite, it's an interesting question. I'm not, I don't think it's common or I haven't seen much of it or any of this, so I'm assuming this is in the context of quantum error correction where you have a logical state and you have a physical state. I think that one reason why this may not be seen much, this is certainly very understudied because it's kind of hard to describe which operations are fault tolerant in a certain qudit dimension versus a different qudit dimension. So the conversions between that is quite understudied. I'm very interested in this question as well. We're hoping to work with a bunch of different qudit dimensions at once in the same framework, but there's lots of theory that has to be worked on about how stabilizer fragments of quantum computation change when you go between qudit dimensions.
Cool.
Okay. So there is work that is going between these qudit dimensions, but most of that work has not been about fault tolerant settings. So that doesn't answer this question. But gosh, I'm excited. So I just introduced this notation back here. This is just a choice of notation for the CX gate because it's still not quite standard how the circuit model is drawn in for qudits. And specifically, this lambda has a more general interpretation. This is so this lambda notation is that it applies the gate U to the target to the power of control number. So this, in other words, applies the gate U to the target C number of times. And just like in the qubit case, these three gates generate the Clifford group for any prime dimensional qudit. So it's nice for prime dimensions because you don't have to worry about whether each element that's not zero in the integers mod D always has multiplicative inverse, for example. So you always you can have a systematic generalization. So qudit generalizations of X and CX gates are not necessarily Poly or Clifford. And on the previous slide, I showed an example of CX that was Clifford, but many CX you can get if you had just chosen a slightly different but quite reasonable generalization would not be Clifford. So to start with the X gates, I'll just show them for qutrits because this will get some idea. But if you have 3 qutrit basis states, the poly ones ascend 0 to 1 to 2 to 0 and 0 to 2 to 1 to 0. And the Clifford ones, because there's only 5 possible permutations of single qutrit basis states. So if you're permuting elements of 0, 1, and 2, you get 5 possible permutations. And these 3 are Clifford. So these 3 that swap 0 and 1, but keep identity on Ket2 state, or the others swap 1 and 2, or 0 and 2, these 3 are Clifford. But in the qubit case, you only get one non-trivial X gate, which swaps 0 and 1. So non-trivial meaning not identity. So as you get more qudit dimensions, you get more weird-looking single qubit permutation gates, which you could call X gates in that they swap around these permutations, but they're not poly and not necessarily Clifford either. So for these controlled gates, this is just, for example, let's just say we're controlling on the Ket2 state and only applying the poly X gate, so also just called an X plus 1, only applying this X gate to the target if and only if the control is in the Ket2 state, and doing identity on the target otherwise. So more generally, if you had multiple controls, I refer to this as dit string controlled Toffolis to distinguish it from other possible generalizations of Toffolis. And one kind of interesting question is what level of the Clifford hierarchy is needed for just these dit string controlled Toffolis? It is an open question because later in this talk, we'll talk about what level is sufficient, but we don't know if that's the best you can do. So for to get into some more general language we could use that maybe more consistently describes these prime dimensional qudit computations. This is a crash course in the ZX calculus, but these parts shown here still work for qudits. for prime dimensional qudits. And I'll show the full rule set in a few slides. So this copy map, it's called copy because it copies computational basis states. It does not copy any state, which wouldn't be possible due to no cloning theorem. But and this is used as a in ZX calculus. This is notated this way. And this just follows from the definition of the green spider with any number of legs. So the green spider with any number of legs. Thanks. Getting my pen to work. There we go. Yeah. The green spider with any number of legs is defined as here. This part just that part just is these dot dot dots mean that it can be any number of legs. So in this case, can be 0 legs or 1 leg or more legs, any number. So and the interpretation of this diagram with the inputs on the left and the outputs on the right, for qubits, it's just looks like this. Let's say that we have n inputs and m outputs. Then we have this would be the bracket notation definition. So this is the definition of this green spider. In black and white drawings, we would just have if it's a white colored spider, then it would, then we also call it the green spider. Just say if you want to print in black and white or draw it like this or something. So this green spider, or it's also called Z spider, because it collapses these things to the Z basis, or is defined this way. It's certainly non-unitary because it's collapsing to these two bases, for example. You could think of it this way. This alpha here is a phase. So if you have a 1 input, 1 output Z spider with a phase alpha, that's a Z alpha gate, which is your normal diag, like 1, 0, 0, e to the I alpha, which is the rotation about angle alpha, rotation of angle alpha about the block sphere's Z axis, for example. This generalizes to qudits. There's a few different notation, but you could use the notation, for example, that make this alpha a vector, so that the first component is the phase for the 1 state, and then let's call this alpha 1, and then plus e to the I alpha sub 2, the second component of that vector for the 2 state, and so on. So likewise, you also have this X spider, and the X spider's general definition is just the same definition, except instead of ket 0, ket 1, ket 2, and so on, it's the eigenbases of the X operator instead of the eigenbases of the Z operator, so the eigenvectors. What it does on computational basis states is that the red spider with, say, any number of inputs and 1 output is defined to be an addition modulo D of all the basis states that are input. This brings us to the definition of CX gate. So the one we saw before, the Clifford CX gate. And this has a nice interpretation of as a sum gate, because you could see that you're just copying the control and then adding that one, the copy you made that you're not just forwarding on to the target, adding the modulo D. And actually, this is not true. This is only true for, I wanted to mark that. This is only true for qubits. So this part is only true for qubits, that if you reverse the direction of this edge, then this equality holds with the calculus defined this way. And the reason is because the CX gate is self-inverse for qubits. So if you do the CX gate twice for qubits, you just get identity. But if you do the CX gate twice for, say, like qutrit, you don't get the identity. You have to do it 3 times to get the identity, for example. But there is a way to define the calculus such that you don't have to worry at all about the directions of these edges, thankfully. It just means we have to just have a slightly different definition of the X spider, and then we're all good. So in practice, you can choose whichever versions of the calculus that is most convenient for you. And so that's a good example because this is the choice of letting you bend the wires however you want. So that property, maybe I'll just draw a bit first. If you have like any kind of conic, this is a property called fleximity in the graphical calculi literature, but it just so if you have like whatever bending wires, it's called fleximity, I guess technically, but it's a technical term, but it's called fleximity as a technical term, but you can also just think of it as only connectivity matters. So I've just drawn 2 diagrams that are the same up to so all the connections are the same. The only difference is that I can rearrange or move them around as however I want. So this is also something you think of like you see in like tensor networks. One thing to note is that these edges are undirected. In this case, we would be directed if we had chosen to define the calculus to not have these for the direction of the edges matters, but we can always redefine it so that they don't matter. So with these undirected edges, it's just a graph. When this OCM or only connectivity matters rule just lets you bend them around however you want. So
Lia, can I jump in with?
Oh yeah, go ahead.
Questions that have been asked in the chat.
Mm-hmm.
So earlier, shown us what is discrete phase space.
Sorry, could you repeat the question?
What is discrete phase space? Not sure if that came up in the talk.
It didn't come up in this talk, and it's actually something in a different field. So maybe I should not answer that. I'm not qualified to.
So we have a question from Jacobs. This was on the part you were explaining before. Aren't Pauli's Clifford by definition? Isn't the X gate a Pauli?
Yes, both of those are true. So yes, the X gate is a Pauli, and also the Paulis are included in the Clifford. So this Clifford hierarchy, every level is included in all the levels above it, but not the other way around. So the Paulis are the Cliffords, and all Paulis are Cliffords, but not all Cliffords are Paulis.
Cool. And we also have a question from Shashi saying, for a qubit, we have a block sphere to visualize. How could we visualize a qutrit or in general a qudit?
This is quite a complicated, this is actually really complicated because you have this, for qubits, you just have this nice coincidence where just this property that SU2, so single qubit gates, is in some way isomorphic to SO3, which is rotations in real 3 dimensions. So 3D rotations of real, say, real value matrices. So this means that we can visualize single qubit gates as just rotations on this sphere, which is like described by like real 3D, real numbers in 3D. So there is some papers that are in these higher dimensional geometric block spheres, and it's just extremely complicated because the number of dimensions just shoots up really quickly. Mm-hmm. So it's no longer a 3-dimensional thing, and I have trouble wrapping my head around it.
Yeah, I guess it's like it's really difficult to visualize like a 2-qubit state even, just kind of also.
It does have the 2-qubit block sphere, which is really great. It's quite useful. So, but you could visualize at least the Clifford fragment of the quantum computation quite nicely for prime-dimensional qudits. And we are working on the non-prime case as well. It just has a lot of edge cases. And it's not easy. So for qubits, I screenshotted this from this paper, the rule set of qubit ZX calculus that is complete for all any stabilizer maps on qubits. So I left out two rules. One is something involving a scalar. Give me a sec. One is like this diagram with no inputs and no outputs is some number, is the number one. And another rule I left out is not necessary for completeness for stabilizer ZX, but adding that rule gives you completeness for all possible linear maps on qubits. So what I mean by completeness is a quite precise property of quantum graphical calculus that in any linear maps any two circuits or computation doesn't have to be unitary. Any two ZX diagrams that evaluate to the same linear map. So say if you were to compute the matrix, for example, if they are equal, if those two linear maps are equal that they compute to, then you could always derive them using just the rules that are in the calculus. So in the qubit case, there's 8 rules. So it's of course not possible to do this efficiently in the general case, because otherwise, if we could classically simulate quantum computation efficiently, we would have that would break something in complexity theory, I'm sure. But for the stabilizer fragment, we can do this efficiently. So let's see, yeah. So specifically, we have a unique normal form that we could simplify any two equal diagrams to, and then you just take the path of rewrite rules that you apply. So any of these in this box here, and it will take you to this unique normal form of one diagram, and you can take another diagram equal, and if it gives the same unique normal form, which they will be the same if they're the same linear map, and they will be different if they're not, then you're good to go. So it's quite straightforward to use. I would say that each of these rules has a pretty straightforward, is quite concise and simple. So I can give some intuition for each of these rules. So S1 is this spider fusion rule, which says that if you have any two, if you recall the bracket notation definition of these Z spiders, this is really easy to prove with the bracket notation, that if you collapse to the Z basis in two different ways, and then you connect them by at least one wire, then you're just adding up those phases. So one example is like if you're doing a Z alpha gate, and then the Z phase gate of beta, then total phase is alpha plus beta. So this S3 prime rule is just because you can bend the wires. However, you can also imagine them as straight wires, and if they were straight wires, then if you have a Z phase gate of phase 0 or an X phase gate of phase 0, then you're not doing any gate at all. It's just identity. this B1 gate we already saw is like copying computational basis states. So this one input, two output spiders just copy on here. In this case, this is ket 0. And this B2 prime rule is a bit more, is a bit harder to parse at first. But it's like if you first did copy and then addition on the two outputs, modulo D, in this case modulo 2, then it's as if you first did the addition modulo 2 of your two inputs and then copied the output. So that's also quite straightforward. And this Hadamard decomposition is a quite simple diagram. This pi over 2 faces that just means the S gate for qubits. It just means that we don't need to use the Hadamard gate as a generator, even though it's very useful to, of the calculus. We could always express the Hadamard gate in terms of just green and red spiders, like this. And the last one here is color change, and this one is that you can color change between a green spider of a certain face and the red spider of the same face, just by conjugating by Hadamards. And it's because this Hadamard is the gate that changes between the Z and X bases. So that's quite nice to. So for example, let me draw. For example, if you conjugate an X gate by Hadamards, you get the Z gate, and if you conjugate the Z gate by Hadamards, you get the X gate. I will also just mention that the one rule that I didn't show, that's not just like some scalar, is conceptually it's just that if you rotate about the Z-axis of the Bloch sphere, then X-axis, then Z-axis again, then there's always exists a choice of other angles related to those three angles that you rotated about, and that it's an X-axis rotation, then Z rotation, then X rotation. And so so that's quite nice. And for Qudits, actually, we've succeeded in really boiling down as much of the rules as we possibly could. And these rules used to be extremely more complicated, as was the qubit rules used to be way more complicated. And I think we've boiled down to the essence of what rules are needed. So I'm actually very pleased that these rules are so simple. Or by simple, I mean, because you're dealing with much bigger matrices for Qudits, it's kind of, it can be a bit frustrating to work with the matrices. So I'm kind of very glad that we've got this software now, that we're just, we put up this, we're working on this software version of PhysiX, which is the Python tool for ZX calculus, but we're calling it DizX because it's the Qudit version. We didn't want to just put in the qubit version to not break backwards compatibility. So anyway, these Qudit rules are really visually similar to the qubit rules, which is good because it means we're on the right track. And these are near minimal. The qubit rule is near minimal, which means that most, if not most, of the axioms we can prove we need to have. So that's quite exciting. And it's quite simple. And you can derive all the other possible rules to simplify or rewrite or have any equalities of Clifford circuits or anything. It doesn't have to be circuits. Just with these rules. I won't get into the definitions of all this Qudit stuff because I don't think it's super enlightening, but it will be in our upcoming paper. So, but I can give one example, which I think is quite cool. So here, this is the GHZ state. So, oops, I failed to select the pen. Here. So this is the circuit for the GHZ state for qubits, but you could also construct a GHZ state for Qudits just the same way. Just replace the ket 0 states are still the same. The H gate is still the same, and just replace the C naughts with the Clifford version of the C naughts. So what that will look like. So ket zeros are these things, and then the Hadamard gate looks like this. Yeah. And then the C naught gate, I'll just use the one where you don't bend the wires. So then I guess to show if this one's Hadamard dagger or Hadamard. In this case, it doesn't matter which one it is because we're acting on the ket 0 basis state, so they both do the same thing. So strictly speaking, the catmord gate is the one that changes green to red in this case.
We have a question about the spider notation.
Oh yeah, go ahead.
From Ron. Does it have an assumed left to right time vector?
Time vector? No. So this is what I mentioned earlier about the directionality of the edges. So because we had chosen to define the calculus such that all the directionality of the edges never matters, so only the connectivity matters. It doesn't matter the directions of the edges. So no, there's not an assumed time vector. If you draw it as a circuit, I guess you are implicitly assuming left to right. But or say left to right, or if you're drawing from top to bottom, bottom to top, you may have some convention that you prefer to show order of operations, but it's kind of nice that you don't have these restrictions of the edges mattering. So for example, you can see that, for example, from here, by spider fusion, you could fuse these two, for example, and then you could unfuse them, but in the opposite order. So you could see from just spider fusion rule here that that some of the things that commute to each other is just follows directly from those rules. Whereas in the circuit notation, it takes some experience to think of this. So for this diagram, this is so far I've just literally translated everything from between this, just every gate one by one. And then let's just say we want to first do a spider fusion rule. So let's just say we do it like here and here. Might as well. And then let's also just color change this. I'm doing multiple steps at once because I'm lazy. So this color change will change this red spider and consume this Hadamard to become a green spider, or sorry, black to white. And then this fusion will now look like this. And this will look like this. And then we can just say, well, when I say, I mean just apply the rules again. Let's just say we fuse this, and let's also fuse this too. So maybe I should have undid that. There we go. Let's just say we fuse these together, because you can fuse if they're the same color, and if they're the same color and connected by at least one light, you can just fuse them together. And then the order of operations doesn't really matter as long as we get to what we want in the end. So that's why we're kind of cheating and doing multiple at once. So these ones are just identities because it's a X phase gate of phase 0. So this is they're just a single wire, and this is what you get in the end. So we've shown that this GHZ state in any prime qudit dimension is just equal to this diagram. And this diagram we know, well, from the definition of these spiders, we know that this is, there's no inputs. So this is like ket 0s plus ket 1s. I'm ignoring normalizations here. I've just done that throughout because it makes the talk less bureaucratic, and then for up until ket d minus 1s. So this is the state that we get. And this is just the standard qudit generalization of the GHZ state. Actually, this proof actually works in all qudit dimensions, not just primes. But I haven't talked about non-prime qudit dimensions. That's why I've just said primes for here.
Cool. Can I jump in with a few more questions? Mm-hmm. There was a question from the Friendly Crow. Is there a limit to how many states we can have beyond qutrits at a physical or measuring issue? And then yeah, we had a response from Jacob in the chat saying there's physical systems with an infinite number of available states like hydrogen, but individually addressing them becomes intractable.
Yes, it's more of an engineering challenge, but there's no physical reason why we couldn't just address a lot of states at once. So you could measure, you can measure qutrits or Qudits, so D equals 4. So I've seen my collaborator, Shusheng, who's a postdoc in the physics department at Oxford. in Peter Leake's group. They worked on superconducting quantum computers, and yeah, they can measure whether a qubit state is in ket 0, ket 1, ket 2, or ket 3 at this, and then they have some machine learning to figure out which one it is.
Cool. Yeah, we have some more questions. Alberto asks if there's any reference to get started in ZX calculus.
Yeah, there is. What's the best way to give this link? I'll put it to you in the StreamYard chat. So
yeah, and I can put it into the
okay.
live chat.
Well, let's see. So this is one reference. I just put it in the chat. This is a new one that just came out, I think this week or really, really recently, this month. Yeah, really this week. But I guess I would recommend it if it's a basic reference. So this is probably the most introductory reference that's also free to read. That's not a textbook. So I would also recommend. Let me just get the link for it. So the first was a set of lecture notes by Bob Cooker that he made for Arthur Eckert's course at University of Oxford, and then as a guest lecturer. And the second one is a more advanced resource that's a review by one of my PhD supervisors, John van der Wendering, who wrote this review intended for people who are already researching quantum computing. And the first one is for more intended towards students, and I think are quite good. There's also free textbooks. So there's the Quantum in Pictures new textbook that came out, I think, last month, and that's intended for high school level. And that whole textbook, I think, doesn't have any matrices in it. It's just diagrams, but they still get to quite advanced topics like non-locality and anyway. So that is really cool. I hope you guys can see a copy of the textbook because it's quite fun. And then I would also recommend Picturing Quantum Processes, and there's a sequel textbook to that being written by Alex Kissinger and John van der Wendering. That's called Picturing Quantum Software, but that's not published yet. But they've been working very hard on it, so a lot of it is written. Yeah.
So there's lots of things to come. So yeah, we've put those two links into the live chat, and we'll also put them in the video description if anyone wants to find them later.
Also, I should add, I'm working on a tutorial as well. This was my part-time work at IBM Quantum Education in collaboration with James Weaver. And so this tutorial, I wanted to improve it a bit more, and there's a lot more things I wanted to add to it before putting it out, but I'm quite excited to think we hope it can come out to just be publicly available online in the coming months.
Great. Yeah. So people can keep an eye out for that. I guess if you follow Qiskit on social media, then it can stay updated on new things coming up. Great. And we have one more question at the moment in the chat, which is from Ixchel. Is it possible to do circuits with qudits in IBM quantum computers, and how big can D be? If not, how about simulators in Qiskit, and is there a plan to integrate them into Qiskit in the future?
I wouldn't know how to answer this question because I don't work on the hardware side of qudits at IBM, but I know that there has been work with qudits, with qudits, and because of open pulse, you can, and I think people have worked on it and shared, because of open pulse, you can design qutrit pulses, for example, directly with open pulse. Because it's open sourcing the operations sent to the hardware. So I saw a hackathon project where the students used open pulse to design qutrit kits.
Cool. And Jacob has also commented that you can always simulate a qudit with qubits if you want to. So you can do that as well. But I think there might be plans to integrate qutrits into Qiskit, but I'll look into it and ask people, and then maybe can leave it as a comment afterwards. Yeah.
Yeah.
Cool.
Oh, Maria, I wanted to ask. So I may have prepared way too many slides for this, and I wanted to I don't mind keep going, but I don't want to I don't want to like talk all the time. So I wanted to ask you, what do you think? Should I? So
yeah, we can keep going a bit longer. Like I think 10-15 minutes is fine.
okay,
If,
that's a challenge.
yeah.
Okay. Let's see. So just to get an idea of, so I may go through some of these slides faster, but no worries. It's just, I'll just point out which parts I think are interesting. So the qutrit T gate, for example, looks like this. And actually the T gate, so just if you were to choose a single qudit diagonal gate in the third level of the Clifford hierarchy, the T gate is actually special just for qubits and qutrits, and it actually has a systematic definition for prime dimensions higher than 3. You could also choose this gate, which you just add a single non-Clifford gate to the Cliffords, and you get universal quantum computation. So this gate looks Clifford, but it's not, because it's 1 minus 1 is Clifford for qubits, but 1 minus 1 is not Clifford for qutrits. So yeah, and so this gate is nowhere in the Clifford hierarchy. And quite interesting, Clifford+R is a strict subset of Clifford+T. So you could simulate this OR gate with enough T gates, but it's kind of awful. It's like 39 T gates. So, more generally, I've been thinking lately about this dth root of Z gate. So this is just U sub 2 comma 1, where this right here, this is U just let M equals 2 and A equals 1. So this is work I'm gonna present in Japan next week. That's just that's a single qubit diagonal gate defined as the d squared root of unity, basically, coefficients. And this gate is in the dth level of the Clifford hierarchy, and it's enough to build any prime qubit dimensional dit string controlled Toffoli. So and it coincides with the qutrit T gate so for d equals 3, but it's a separate thing for higher prime dimensions. So the construction, and we don't need to go to the proof here, but we can build a Ket0 controlled X gate, which is non-Clifford, and out of just Clifford gates and this dth root of Z gate. So this is some proof of why it works, but that's not important. You just repeat this. This is based off a qutrit construction by Bokarov, Rothschiller, and Spohr. But we realized it will also work if you just do it for any prime qubit dimension. And this is actually related to some cool things you could do with qudit gates, is that even if you're only interested in just qubit or binary computation, say your data is binary or something, you could still get some interesting advantages if you use higher level qudits, say, in your physical system. So for example, there was a question just now about if you could you can always simulate qudits using enough qubits. And here, this is the opposite. This is emulation, where just opposite in terms of like you're using qudits to do qubit or binary computation. So here is a binary AND gate. And so it's not possible to do a 2-qubit gate that does the AND if you don't have any ancilla. But for if you just use qutrits, then you can, because you just do this Clifford CX dagger gate, CX inverse gate, and then a Ket2 controlled X-1 gate. And the truth table of this is this thing, and you just care about this, what happens when the inputs are bits, because you don't care what this gate does when the inputs are not bits. And you can get this AND bit of the 2 input bits. And it's not possible with qubits, because with qubits, you cannot just assign the other output other than this AND of the 2 bits to be something, so give it a unique assignment of this other computational basis state such that you could recover what the inputs are. So to make it reversible and thus unitary. So you could also do interesting things with the qubit CCZ gate. I should have cited right here. This qubit CCZ gate, you can emulate it with the qutrit Clifford CX gates, and then so 4 of them, CX or CX dagger, and then 3 single qutrit ART gates. So that's quite interesting that you only need 3 single qubit non-Clifford gates in order to do a qubit CCZ gate. So this is the exact same matrix as a qubit CCZ gate. Whereas for qubits, you need at least 7 T gates if you want to be unitary, and you need 4 if you're not allowing non-unitary operations. I'm skipping the part where we built all dit string controlled Toffolis in this gate set, because I think that part is not that interesting. The proof is just kind of brute force going through this computation by hand. But the interesting one of the key parts of the construction, I'll show, I think, 2 key parts. The first one is that you can do this linear stacking of these Toffolis to get linear gate count of linear in the number of controls. So this is a screenshot from Craig Gindey's blog post from 2015. And this same trick, so in the qubit cases, involve like toggling on this control value on and off, but you can do something similar in Qudits. And actually the trick here is just because of this lambda control, you're applying the x+1 gate one more time than the x-1 gate, regardless of whatever the borrowed ancilla is. So this borrowed ancilla is just an empty wire because you need it to do the gates in the decomposition, but you don't care what the input of this was, and it's guaranteed to return in the same, to output in the same state it was input in. So, and this will work for any unitary U that you can build this controlled gate as well. So we can exchange any 2 bit strings. This is just saying that you could build any classical reversible function. So this is any permutation of a dit string of length n to another dit string of length n, for example. So this is useful if you're building like oracles and stuff, or just multiple control gates. And this is a nice bound on the number of gates that you need. And it's within a log n factor of the minimum number of gates that's necessary. I took out this slide actually because it's just a bit too much numbers. This slide is just about how this d3.z gate, we don't know if it's possible to implement efficiently fault tolerantly yet. So this is specifically about if we can teleport it into a circuit. It was conjectured to be based off some numerical evidence, and because this is the case for qubits and some qutrit gates. And if this conjecture is true, then we can do fault-tolerant multiple control Toffolis efficiently. And if this conjecture is false, then it actually is really interesting because we actually don't know which are the gates we can do fault-tolerantly versus which gates we can't. But it would be kind of weird if this was false because it is true for qubits. So this is some theorem about our gate count. Another theorem about our gate count. This is about this is what we call the prime qudit dimension equivalent of Toffoli plus Hadamard for prime qudit dimensions greater than 3. And we didn't find anything in the literature about this, but it was quite straightforward to show that if you were to take this Ket0 controlled X gate, you can construct all classical reversible gates from this gate. Well, actually, it was straightforward, but a lot of different circuit identities, but that works for all prime qudit dimensions. And so you just add one gate, the Hadamard gate, to all the classical reversible gates, and you get approximate universality. That's just like it is for qubits. We actually don't know if this works in qutrits, so d equals 3. That's kind of a special case. It's a bit harder to prove. We can't use the proof techniques on qubits or other dimension cases. So the proof is quite straightforward, but the proof basically boils down to this review on qudits said that these 3 gates are approximately universal for prime qudit dimensions greater than 3, and CX and H are Clifford, and then the last one you can get from the ket0 controlled X gate like this. And so therefore this gate set is universal. If you allow this, you just need this one ancilla qubit for doesn't matter how many other qubits you have or qudits you have, and just always keep it in the ket0 state. And then you can do this. And you can still, for example, you can also do the X gate if you just do the ket0 controlled X gate with your control in that just qudit that you eternally keep in the ket0 state, for example, even though that's a bit silly. So anyway, this is the Qubit version of Toffolis Hadamard for dimension greater than 3, which we were very excited about. I'm so excited we built this is, we actually have a whole calculus for this. So this is if you extend or redefine the ZX calculus to focus on the interaction, instead of between Z and X, you focus between Z and H. And H just corresponds to multiplication mod D. So actually there should be a mod D and then exponent of this A. And so H is, if you, by default, if you don't label this phase, we just assume that this is the coefficient here, this that you're taking the power of, is just omega, the D3 of unity. And in that case, you just get the Hadamard gate if you have just one input and one output. But this is just extending the Hadamard gate to have any number of legs. So I've used this notation of Hadamard gate to be changing from green to red spiders. So if you change from red to green, that would be Hadamard dagger. And multiplication of a computational basis state by -1. Mod D is just 2 Hadamards in any qudit dimension. So in qubits, it's, well, multiplication of 0 and 1 by -1 is still 0 and 1. But in all qudit dimensions, four times applying the Hadamard, so h to the power 4 is just identity in all qudit dimensions. So this is multiplication mod D. If we notate it this way, we can also draw the lambda controlled versions of these CCZ and CCX gates like this in the calculus. So the CCZ gate, you can nicely see is symmetric, and then you can choose which one of the gates you want to be the target of the CCX gate by just conjugating that one by Hadamards. So you just say you color change. For example, you chose the bottom one to be the target, then you just color change this green spider into this red one and with these Hadamards. So that's quite nice. And so if you remove this Hadamard and this Hadamard dagger, then you just get the CCX gate, where the CC is actually this lambda, because of these lambdas, is corresponding to multiplication of the input basis states that are controlled modulo D. And this is nearing the end this is like actually the end of the talk. So I'm quite excited about this. So there's actually, in the qubit case, there's 3 quantum graphical calculi that have a bialgebra rule that's not trivial. So the 3 calculi are the ZX calculus, the ZH calculus, and the ZW calculus. So these are 3 different choices, all of which are complete. You can just, of which graphical calculus you want to use. Which one you want to use may depend on which applications you're interested in. So the ZX calculus we've talked about so far, and traditionally, so in the earliest days, people were mostly using it for quantum circuit optimization and measurement-based quantum computing. And nowadays, people are using it for many other things as well. So, and the ZW calculus is another calculus that this one is really useful for, let's say, like sums, because if you wanted to sum ZX calculus diagrams, then the addition just becomes external to the calculus, and then you just kind of get stuck there if you want to reason about the sums too within the calculus. And the ZW calculus, because this W spider kind of corresponds to, say, like Noon states in quantum optics, yeah. So this quantum, you can reason about quantum optics. So this is the bialgebra rule between like the photonic W spiders, for example. That each of these is a beam splitter. So, but something that was quite quite cool is that you can combine these calculus and you get these calculi and you get more than just the sum. So you could, if you combine zx and w, these generators all in the same calculus, you can get the rules between z and x and also rules between z and w, but you also get these new rules between z and x and w that the interaction, we call it the trialgebra rule. That's like the essential one. And what this is useful for is that, say, I mentioned every time, let's say you wanted to differentiate a quantum circuit, say in like quantum machine learning, then every time you differentiate a circuit in ZX calculus, you could just get a sum of ZX calculus diagrams. But if you could do it entirely get a single diagram out if you just do it in quantum machine learning in the ZXW calculus, just like this. And so you could also do like Hamiltonian exponentiation, so because this involves these sums. This is our newest result. So with this, we prove all equations for qudits, any qudit dimension, including non-prime, that's derivable in Hilbert space. And in short, so if you have any two ZXW calculus diagrams that are equal, it could be ZX diagrams, ZW diagrams, doesn't matter. Any two diagrams that are equal, mathematically equal, if you interpret them as linear maps, can you prove it using just a finite set of rules, axioms of the calculus? And the answer is yes. So we were extremely excited about this because this is the first completeness result for any quantum graphical calculus that's beyond just a universal fragment of cubic quantum computation. So the first completeness result for beyond qubits for any universal fragment of quantum computation. So we're already working quite hard on the follow-ups to this. We're working on this for photonics as well. So I think this is quite a big deal because there's just so much more we can do now that we have this very powerful, like I guess not just software methods, but techniques. So I'll just put on my summary slide and yes, there we go. And thank you all for listening to the talk, and hope I can answer any questions.
Great, thanks for the talk, Lia. That was really good, really interesting stuff. And yeah, I think people in general are much more familiar with qubits than qudits, so I'm sure everyone will have learned something new, well, lots of new things. Yeah, so yeah, write in the chat if you have any final questions. One of them, which I think you mentioned a bit in the introduction from David, is what are the real and practical benefits of qudits for quantum computing? So maybe you could summarize those again.
Yeah, I mentioned this at the start. Maybe it's easier if I, oops. Maybe it's easier if I just go to that slide directly. Yeah. Well, the review that I mentioned on qudits, even though it's a few years old, is still quite good in showing a lot of different reasons to study qudits and what's been done there. So I actually haven't mentioned, like, say, quantum communication. There's a whole review on qudits for quantum communication. So you may want to better control qubits, or for, say, quantum error correction or magic state distillation. In fault-tolerant quantum computing, you can get some better thresholds or some better asymptotic behavior with qudits. Or at least that's been seen. There's some research papers on that. There's people are interested in this emulation part as well in, say, quantum computer architecture, because you have these extra states and they can help you optimize your operations at the hardware level. And you can also have some interesting, like, say, qudit native problems that you may be interested in. So, for example, there's a single qutrit algorithm that determines efficiently if the parity of a permutation of length 3. So if you have, say, like, is that an even or odd permutation? You can I have a recent paper on qudit W states. So yes, it should be up online soon. So this is quite interesting. I'm hoping I'm open to ideas about like applications for this, because this is a way to construct qubit and qudit generalized W states using qudit, Clifford+Z. And the idea is that if you're doing, say, leader election protocols in quantum communication, then you actually require the W state to do this, to do a quantum leader election protocol. Say that could be a prerequisite for, say, calculating the minimum spanning tree of some graph or something like that. And so constructing these W states, I think, is quite interesting, because in quantum communication, if you are relying on a giant entangled state in a quantum network where each party, say, has one particle, you can maybe do something more interesting kinds of protocols if your local dimension of the particle you have access to as you're part of this network is higher than just 2. So maybe if you have like 3, for example, you could like indicate your vote for like 3 different options instead of just 2 or something like that. So
Cool.
So that's a quite hand-wavy answer to this. But I would just say check out the reviews. They're quite thorough.
Mm-hmm. Great. Thanks. And we have one more question from Ron. Can you summarize why prime dimensions are so special?
Yeah. On one hand, I want to say I hope that they're not that special, because we're trying to work on the non-prime dimensional case.
Mm-hmm.
Although our technique will be quite different, or will be a bit different. But let's see. So let's see. Yeah. I had this slide I wanted to show. Yeah. So, for example, things like multiplication mod D, these things are natural in prime dimensions, but you actually get some problems when you have non-prime dimensions, because you need to make sure that whatever axiomatization you're working on has to incorporate this information about what is the multiplicative group structure, or it's just not a group, multiplicative structures of each qudit dimension. So the reason why we can just uniformly define this calculus with the same shapes of the same diagrams, and you just interpret them over a different qudit dimension for prime qudit dimensions for ZH calculus, like -1 mod D is just these 2 Hadamard gates in a row. But if you had, say, D equals 4, then you could have that 2 multiplied by 2 modulo D, so modulo 4, it gives you 4 mod D, which is 0. So you could multiply 2 non-zero things and get something that gets 0 mod D. And this wouldn't happen in prime dimensions. You can't multiply non-zero things and get 0. So that's definitely something that really complicates this. I don't know how to generalize this construction to non-prime dimensions. I've tried, and at some point I succeeded in some part of it for dimensions 2 to 11, and it's just my trick didn't work for dimension 12. So whatever it was didn't work. So it's quite interesting open problems here.
Great, thanks. Yeah, I think that's all our questions. Thanks for the detailed answers, Lia. Yeah, so just as we wrap up, thanks everyone for joining from all these different places. We will have another seminar next week. That will be at 12 p.m. Eastern Daylight Time. I think clocks are changing soon in the US and then later in other places as well. And that will be a talk by Sandro Miano on engineering nonlinear Hamiltonians with flux-tunable superconducting circuits. And if you want to stay updated on our seminar series, then make sure to subscribe to the YouTube channel, where we also post lots of other quantum computing content for a range of levels. And yeah, just a final reminder as well about the Women in Quantum seminar series that we have. The link is in the description, so do check that out. And yeah, I think that's all. Do you have any final comments, Lia? Anything you want to draw the attention of the audience to?
I had some links, but maybe this would be better. after. The main thing is I just wanted to shout out or mention the quantum conference, the Quantum Science and Engineering Education Conference. Get the word out about this call for papers and posters and talks. So I can probably just send you a link.
Yeah, great.
Yeah, so I guess that's not a quite particular audience, but yeah. But more generally,
yeah, we posted it in the live chat so people can access that. Yeah.
So thank you for hosting this. I had a lot of fun, and the questions you guys had were really, really good.
Great. Yeah. Thanks for the questions, everyone. It's great to have it interactive, and that's why, well, all the seminars are recorded, so you can access the previous ones on YouTube, but we only get this live interaction if you join live. So it's really good to have you all here. And we have some nice comments from people saying, Jacob says, thank you, Lia, great talk. Shoshi says, thanks, amazing talk. Ixchel says, thanks, Lia, Maria, great talk. So yeah, thanks everyone for joining, and we will wrap up there and see you next time.
Happy International Women's Day, everyone.